Welcome back. Today we're finally going to add some new hardware to our Intel 8188 computer, but first I would like to thank JLC PCB for sponsoring this video. I'm going to tell you a little bit more about them in a minute, but first let me show you what is going to be the new hardware I've just mentioned. It is this little SD card working as the hard drive in our computer. Our multi-I/O device, which is this Raspberry Pi Pico here, will communicate with the card using the SPI protocol. I added the pin header here, which has all required signals for this adapter. I had to modify the adapter slightly by removing its voltage regulator, as it was probably designed to work with the 5V logic, while the SD card works at the 3.3V levels. The Pico also works at 3.3V, so we can already provide this voltage supply directly to the card. The other small IC on this adapter is a set of buffers to shift the logic levels, just as we did here by using these 74LVC245 between the Pico and the 5V Intel logic. Here they are completely redundant. Just to wrap it up, I could as well solder the SD card socket directly on this PCB without using any components in between. Okay, now the question you may ask is, what's on the card? It's not blank, no. It wouldn't be too exciting to read a bunch of zeros during the tests, would it? I've installed MS-DOS on this card. To be precise, I installed it on a virtual machine and then copied the whole disk image onto this SD card. Of course, we're not going to boot DOS from this card anytime soon. We don't even have any BIOS yet to initiate the process. The main reason for having MS-DOS here is to have a proper real-life structure of the data on this disk in order to have something to work with when implementing our BIOS. Today, I hope to read only one sector from this SD card, the most important one, but we'll talk about it later today. This video is sponsored by JLC PCB. Apart from regular PCBs, they also offer flex PCBs, PCB assembly, 3D printing and CNC machining. The best quality for very affordable prices. If you have any electronic project in mind, there is one place to go, jlcpcb.com. Currently, JLC PCB offer a $20 discount for 6-layer PCBs with via-in-pad technology included for free. Via-in-pad allows vias to be placed directly on the copper pads, which gives you better design flexibility and requires less space on the board. Check them out at jlcpcb.com. I can't wait until I finalize the design of our computer's board and show you the PCB manufactured by JLC PCB. This test is not going to involve the Intel CPU or, in fact, most of this computer. The sample program for the Pico is going to simply read the card after power up, spill out some information on its standard output, which is configured to be this serial port here. I mentioned briefly initialization of that port working as the output in the previous video. And then the program stops. It's just a test and I want to keep things simple for now. Okay, so that's the hardware part. Now let's talk about the software. Fortunately, we don't have to implement the whole SD card protocol ourselves. We're going to use an open source library, which has quite a long name, but at least the name tells us everything about the library. It has everything we need and even more. As the name suggests, not only it supports SD cards with the Raspberry Pi Pico using the SPI bus, but also implements the FAT file system. That's why I said that it does more than we need, because we don't need the last part. All the disk controller does is the low-level operations like reading or writing data sectors. The file system is a higher-level structure imposed and implemented by the operating system. Our Pico works only as the disk controller at the low level. Fortunately, both features of this library are nicely separated, so we can easily use only the SPI part. And, as usual, if you check out this test code from my GitHub page, this library will automatically be included as a submodule. Okay, so let's have a look at our code. It's very simple. All the hard work is done by the library, but let's have a look at the main function first. So the first line is to initialize the standard output, standard I/O. It makes the serial port a default console out, so anything we later printf will be sent to the serial port, which is connected to my computer. I use this USB dongle to do that. The next line initializes the library, the SD card library, which is included here at the top. That's the only header file we need. We'll come back to these later. Then after initializing, we get the first SD card in the system, the only one really, but the library allows us to use multiple cards. And then we initialize the card. The result is an integer. If it's 0, then everything went fine. Anything but the 0 means error. So we are displaying it in this line, init result, and the number returned by the init function. Then additional proof that we can access the card is to display a number of sectors which the card can hold. And that's the second line. Then we define a buffer of 512 bytes, which is the size of the sector, and the whole code which reads our sector from the card is this call to read blocks. We specify the buffer which we want to have the sector in, the first sector, which is 0 in our case, and how many sectors we want to reach. Currently it's only 1, and then in a simple loop we display all the bytes from this buffer in hex breaking line after 16 bytes. And that's it. In the main function, we need to define how the Pico talks to the SD card. So we need to tell the library where it is. There are some structures which define which controller we use, which pins, and the speed and the other stuff, what's the protocol, we use SPI in our case, and so on. Everything's well documented on the GitHub page of this library. I'll give you the link to it in the description. The only thing the library expects from us are these two functions. So first just returns the number of SD cards which we have. In our case, that's just one structure, so it's going to return 1. And the other one expects us to return the pointer to the card specified by this index. In our case, only 0 is allowed, otherwise we'll return null. If not, we are returning the pointer to this structure. And that's it to configure our SD card library, and that's the whole code in this file. Let's try to run it. In order to do that, I already connected the output, our serial port output, to my computer. I showed you this a minute ago. I'm going to use PuTTY. The USB dongle is configured as COM3 on my computer. Let's open it, maybe extend the window a little bit, and let's turn our computer on. Look at that! We have some data on screen. We have read a sector from the SD card using our Pico. I'm going to copy that data out of the PuTTY window and save it somewhere so we can have a better look at what we read. The first sector on every hard disk is the most important one, and it even has its own name, the Master Boot Record, or the MBR. That's one of the few TLAs, or 3-letter acronyms, which we'll mention in this video. So, this MBR is the first sector ever read by the BIOS in an attempt to boot the operating system from the disk just after the computer powers on. At this point, I'd like to make this disclaimer. Since we're talking about the old technology from the 80s and the 90s, whenever I say BIOS, I mean whatever was in the ROM memory of the old computer motherboards. Today it's called the legacy BIOS, in contrast to the new one, UEFI BIOS. Also, the MBR, the Master Boot Record, was only relevant to the old legacy BIOS. Today its purpose is served by the GPT, or GUID partition table. Okay, so why is the MBR so important? Let's have a look. As I just hinted, it is the first portion of the data ever read from the hard drive when the computer starts. It has two distinct regions with their separate purpose. The first part, which starts at the beginning of the sector and can take up to 446 bytes, is a program which the BIOS executes straight after reading this sector from the disk. So that is also what we will need to do in our BIOS implementation in the near future. This program's job is to look at the second part of this sector, which holds something called a partition table. It starts from the offset of 446 bytes or 1BE hex and is 64 bytes long. The last 2 bytes of the sector following the partition table are the boot signature, the constant values for the BIOS to recognize that this is a correct MBR. They have to always be 55 and AA hex. If the BIOS finds any other values there, it should abort booting and you'd see this boot failure, non-system disk error message on your screen. Hard disks can be divided into smaller logical volumes or partitions. In MS-DOS and Windows, they would be assigned separate disk letters like C, D, and so on. The letters A and B were reserved for the 2 floppy disk drives, by the way. So, this 64 bytes close to the end of the MBR is the partition table, which defines how the whole disk is divided into volumes. It is really an array of 4 16-byte long entries, each of them describing one partition. It may look like you could only have at most 4 partitions on one disk, but there is still a way to create more than that. We'll see that in a second. Before we look at the layout of the partition entry, we need to talk more about how the sectors on the disks used to be addressed back in the day. In our test code, we simply used one number, 0 in our case, to address the very first sector on our disk. Unfortunately, it wasn't that simple at the time. We need to introduce 2 more 3-letter acronyms to the story. The first one is the CHS, which stands for Cylinder Head Sector. Let's have a look at how a hard drive is built first, because this addressing mode directly resembles the actual geometry of the disk. Okay, so let's open this hard drive and see what's inside. Finally, I managed to open the case. And there we go. Okay, let's have a closer look. We can obviously see the platters on which all the data is stored. In our case, we have 3 platters. Over each side of the platter, we've got the read-write heads, which can freely move. So obviously, since we have 3 platters, each having 2 sides, we've got 6 of those read-write heads. They are very tiny. So let's think how the data is stored on these platters. If you imagine concentric cylinders on each platter, let's say that cylinder 0 would be the outermost one, and the data can be stored on each so-called tracks on each of the platters. So we've got a track around cylinder 0 here over this head, then another track at cylinder 0 on the next platter, and so on. So we've got tracks of data over those imaginary cylinders on each platter, and there is like hundreds, if not thousands, of those concentric cylinders over each. The heads may travel to access the data stored on each track. Each track fits a number of blocks of data called sectors. Each sector is half a kilobyte or 512 bytes, and there is a constant number of sectors going one after another on each track. So to access any data, we would need to specify which cylinder the heads should be over, and there could be hundreds or thousands of them on each platter. Then we would need to tell which head should read or write data. So we would need to specify, is it this head or the other one, or one of those 6? And then which sector we would like to access on the specified track. Okay, so now you know what a cylinder, a head, or a sector is in the hard drive. In order to configure and use a hard drive in your computer, you would need to tell the BIOS the exact numbers of cylinders, heads, and sectors per track of the disk in the BIOS setup mode. All access to the hard drive made via BIOS was then performed by addressing each sector using these three numbers. All of them were packed into a 24-bit integer. The cylinder number was 10-bit wide, with values starting from 0 to 1023. The head index was an 8-bit number, also starting from 0, so the maximum head ID was 255. Finally, the last 6 bits were reserved for a sector ID, but for some reason, sectors were indexed from 1, not 0, so there were only 63 sectors possible on one track. You might ask, 256 heads? Seriously? That would require 128 platters inside the hard drive. And you'd be right, such a disk never existed. To make things even worse, the ATA standard, also known as IDE, which defines how the disk controller talks to the hard drive, allows only for 16 heads. That means that the maximum effective hard drive capacity would be limited to 1024 cylinders, 16 heads, and 63 sectors per track, giving only around 504 megabytes, because the sector always has 512 bytes or half a kilobyte. That's why, at some point, newer BIOSes employed something called CHS translation, which would simulate a different disk geometry with more heads than in reality and thus use up the 8-bit head number more effectively. Due to a bug in all existing versions of MS-DOS and Windows at the time, the number of possible heads had to be decreased by 1 to the range of 0 to 254. This finally set a limit of CHS addressing to 1024 cylinders, 255 heads, and 63 sectors per track, giving a number of 16,450,560 sectors in total, or 8,032 megabytes, so almost 8 gigabytes of the disk space. As the capacity of hard drives was growing quickly, this proved to not be enough, so another addressing mode had been introduced in later BIOS versions. It's called the LBA, which stands for Logical Block Addressing, which is simply just a 32-bit linear sector number starting from 0 and ending at the last sector on the disk, depending on its capacity. To maintain backward compatibility, the BIOS implemented a translation between the LBA and CHS by using a fictitious geometry, and for the disks larger than the CHS limit of almost 8 gigabytes, the BIOS would simply report a maxed out theoretical geometry which allowed for correctly addressing at least the first 8 gigabytes of a larger disk using the old CHS addressing. All of this means that we need to implement both addressing modes in our BIOS, including the translation between them, in order to allow any OS to boot on our computer. Finally, after this slightly long but important digression, we can come back to our partition table, where we can use our knowledge of the CHS and LBA addressing in practice. As we can see, the partition table on this SD card has only 1 out of 4 entries populated, the other 3 are zeroed out. And that's correct, because I created only one partition on this drive when I formatted this SD card. So let's analyze all bits of the data in this 16-byte entry. The first byte carries really only one bit of information. The last 7th bit is set only if the partition contains a bootable operating system. In other words, if this byte is 80 hex, the BIOS can start booting this partition. If it's 0, then there is no OS here and BIOS needs to look for another bootable partition if one exists. The next 3 bytes point to the starting sector of the partition on the disk. As you might have guessed, 3 bytes or 24 bits contain the CHS address of the first sector. In our case, these 3 bytes give us the cylinder number 0, head number 1 and sector number 1. It means that the partition starts not directly after the MBR in the next second sector, but it's aligned to the nearest head, which usually was the case. The next 5th byte is the partition type. Different operating systems and companies use different values. The most recognizable are 06, used by the MS-DOS partitions formatted using FAT file system. 07 is a Windows partition using NTFS, or for example 83 hex is a Linux partition. There are two more partition types I would like to mention: the 05 hex and its newer version 0f hex. Both are called extended partitions. They allow reserving a space on the disk which can be subdivided into 4 more logical partitions. In the first sector of this extended partition, we can find another partition table containing up to 4 more entries. By using this entry type, you can split the physical disk into more than 4 partitions. You can see that our partition is the MS-DOS one as expected. The next 3 bytes contain the address of the last sector of this partition using CHS addressing. In our case, it is sector number 63 under the head number 63, so as you can see, the CHS translation is clearly used, and the cylinder number is 955 in our case. The other 8 bytes are 2 32-bit numbers. Can you guess what they are? If you think that it must be something to do with the LBA addressing, you'd be right, but with one twist. While the CHS addressing before pointed to the first and the last sector of the partition, this time the first number is the LBA of the first sector, but the other number is not the address of the last sector as you might think, but the total number of sectors in this partition instead. In our case, the starting one is sector number 63, and the whole partition spreads across 3,854,529 sectors. These two values should obviously match the data expressed in the CHS format, so let's verify if they do. Since there are 63 sectors on each track, and we noticed that the partition is aligned to the next track under the next head, head number 1, and the MBR is sector number 0, the starting sector of this partition would be 63 sectors away from the MBR. So that's correct. Now we need to do the CHS translation to find the linear sector number for the end of the partition. To do this correctly, we would need to go into BIOS setup of the computer and note the configured geometry of the disk when it was formatted. Since this was done under a virtual machine, I'd need to check what values it assumed for this disk. But we can do some educated guessing instead. Usually, the fdisk tool, which is used to create partitions on disks under MS-DOS, aligns the partition size to the nearest cylinder. That means that if the last head on this partition is 63, we can assume that there are 64 heads used for this CHS translation. Let's finally multiply 956 cylinders, remember that this number is 0-based, by 64 heads and by 63 sectors in each track. The number we get, 3,854,592, is the LBA of the first sector following this partition. But the entry in the partition table holds the size of the partition, so to get the size, we need to subtract the LBA of its beginning, 63. This gives us the size of 3,854,529. Therefore, we have confirmed that both addressing modes data correlate in this partition table entry. In practice, our BIOS may internally use only the LBA addressing, but to make it compatible with the older software, we'll need to use this translation to implement the CHS addressing as well. Speaking of our BIOS, in this test, we simply used the Raspberry Pi Pico to read the MBR from this SD card. The Intel CPU was completely not involved. Therefore, we need to implement a disk controller on the Pico to be available to our computer via the I/O ports. We already tested this communication in a previous video. Now we need to design the protocol we will communicate with the disk controller. Since our Pico will act as multiple devices, hence the name, multi-I/O, we need to split the available I/O space of 128 addresses or 80 hex into multiple areas, one for each device, the disk controller, the keyboard controller, the UART, and maybe even more in the future. My current working assumption is that we would probably not have more than 8 devices implemented, so I'm going to split the available I/O space into 8 16-byte I/O port ranges, each for one device. Now, I'm not gonna try to copy the IDE controller here. It was focused on handling magnetic drives at low level, so apart from the CHS addressing, it also supported many bits we won't need, like seeking a cylinder status, or if the track 0 is found, or if the drive motor is spinning. It is overcomplicated and even uses two distinct areas in the I/O space. There's really no point of mimicking it, because the software never really talked to the drive controller at the I/O port level. It was done via the BIOS, and that's what we are going to do in one of the next videos. Today, let's just find a way to talk to the Pico using our 16 I/O ports. I'll try to keep things as simple as possible, and I'm sure we won't need all the 16 ports. Let's try this approach. At the offset 0, we will have an 8-bit port we can read to get the current status of the controller. We can assign each bit for a separate error flag, including 1 bit for the busy flag. Since the status can only be read, we can reuse this port for writing. This could be the command byte, which, when written, instigates an action chosen by the written byte. The busy flag would then be set until the command is finished and the result, if any, ready. Let's call this port status when read and command when written. The next byte at the offset 1 will be used to exchange the actual data between the computer and the controller. If we read a sector from the disk, we would then read all the 512 bytes of the sector data from this I/O port. I will call this port simply data. Since I can anticipate other commands than just reading and writing sectors, we also should have a port indicating how many bytes to exchange with the controller's buffer. So at the offset 2, we will have a 16-bit port to put the size of the data. Let's call it data len provisionally. Finally, at the offset 4, we need a 32-bit value with the LBA address of the sector to be accessed. I'll name it simply LBA. This totals to 8 distinct addresses, and at least for now, I think it's enough to get something working. So this is how we're going to use this controller. Let's say we want to read a sector from the disk. First, we check if the controller is not busy by reading its status bits. Then we put the LBA of the required sector to the LBA port. Finally, we execute the read sector command by writing the appropriate byte to the command port. Then we need to wait in a loop until the busy flag resets, which means that the command is finished. We should also check the error flags to be sure that it succeeded before reading the sector data from the data port. The length of a sector should appear in the data len port. In case of writing a sector, after making sure that the controller is not busy and writing the required sector LBA, we then write all the data to the data port repeatedly. After doing that, we can start the command by putting it into the command port. Then again, we wait for the busy flag to reset and check the error bits in the status port. That's the theory. Now let's have a quick look at the example code, which would send the read sector command to our multi-IO controller. Let's have a look at the definitions I added here to the device regs include file. So I added these registers. Status and command are in the same offset of 0, but one is read-only, one is write-only. Then we have the data, 1 byte read and write register, then data len, 2 byte, 16-bit read and write, and the last 4 byte or 32-bit LBA register at the offset 4. And at the bottom, I also added definitions of each of the bits of the status register. I am anticipating these with the most significant bit defined as busy bit. I'm not saying that that's the final definition of these bits, but for now, let's work with these. And 2 commands. I defined a read sector command and the write sector command. These are 1 byte, so I just simply decided to use the ASCII code for R and W read and write for these. Let's go now to the code in the init file. First thing we do is to wait or make sure that our device is not busy. So we repeatedly read status register until the busy bit is not set. If it is set, so the result of this test is not 0, we loop back. First thing we do is to write 0 to all 4 bytes of the LBA register, because we want the sector number 0 to be read. Obviously, the LBA is 32-bit or 4-byte long, so we need to do this in 2 steps in our 16-bit processor. First 16-bit is written here using the address of the LBA in the DX register. Then we increase it by 2 to send 0 to the older part or higher part of the 4-byte long LBA. Then we actually initiate the read of the sector by writing the read sector command into our command register. And then we again in identical loop wait until it's done and the busy flag is cleared. The next step is to read the data len. So if it all works like I told you and I designed, the data len at this moment should contain 512 or 200 hex, as this is the size of each sector on our SD card. What we do here is we read this value into the AX and put a breakpoint, because when we test it on our actual computer, the breakpoint will get us into the displaying the state of all the registers like we did many times before. So we can see what's in AX at the moment. Then after we resume, we will actually read the whole sector, all 512 bytes from our disk controller into the memory labeled disk buffer, which we define here in the RAM or BSS section with the same size. Then we use this rep prefix to read the CX number of bytes from the port under DX. So effectively this serves us as a loop reading 512 bytes from the same data register in our Pico. And the last thing is to read the last 2 bytes. So remember the sector size is 200 hex. But if we want to read 2 last bytes of the sector, we would need to add to the beginning of the buffer number 1FE, which is 2 less than the size of the buffer. This will effectively load into the AX last 2 bytes of the sector, which, if you remember, is the magic data, 2 bytes of 55 and AA hex. Then we put a breakpoint. We will be able to see, hopefully, what's in AX at the moment, and then after we resume after this breakpoint, we go into the main function, which simply displays 40 bytes, 10 bytes per line in hex on our LCD. That's to confirm that we actually have read the data of the sector. I'm not going to go into details of the Pico code here in the video, but please remember that all the code is available on my GitHub page for you to have a look. I'll try to add some comments, at least in the key parts of it. Finally, let's test everything together. Alright, so the new code for the Pico is already uploaded. I also flashed the program I just showed you into this flash memory. So let's test it out. Okay, we hit the first breakpoint at the offset of 94 hex. As you can see on the listing, that is the breakpoint after we read the data len register in our disk controller. So the AX register should have the length of the sector. If you remember, the sector is half kilobyte long, so 200 hex. Let's have a look at the accumulator. There you go. 200 hex. So hopefully our sector 0 has been read into the buffer. When I restart our program, the next breakpoint, let's have a look. Is it offset A2? Yeah, that's correct. So what the program did in between those breakpoints was to read that many bytes, 200 hex, from the data register in our disk controller, which is at offset 1 hex, into the buffer in our RAM, which we also declared in our program. After reading the whole sector, then we move the last 2 bytes from this buffer into the AX. As you remember, the last 2 bytes are the magic values, 55 and AA hex, and that's what we should expect in the AX now. As you can see, the AX contains the value of AA55 hex. Remember, when we treat those 2 bytes as the 16-byte value, the first byte is the lower part and the second byte is the higher part of the 16-bit value. So that looks really good. It looks like we have read the whole sector from the SD card into our multi-IO controller in this Pico, and then we successfully transferred this sector from the Pico into our RAM using our Intel processor. To confirm that, when I restart this program, it will go to the main function, which is written in C, and what it does is displays the first 40 bytes of the sector values in hex onto this screen. So let's do that. There you go. Well, it's hard to read because there is no spaces and any formatting, but each byte is represented by 2 hexadecimal digits. So the first byte in the buffer is FA, then we've got 33C0, 8ED0, BC, and so on. It looks like we have our sector read from the SD card into the memory of our computer. I've mentioned that the software back then never accessed the disk controller directly via the I/O ports. It was rather using procedures implemented in the BIOS. That's why it got its name in the first place. It is the basic input-output system after all. In one of the next videos, we are going to have a look at these procedures and how we can implement them in our BIOS. If you found this video interesting, please consider giving it a like, leaving a comment and subscribe if you don't want to miss any of my future videos. Thank you for watching and see you soon.